Oh yeah, and Scott wanted us to all say Happy Harloween together. So 1, 2, 3. Happy Harloween. Okay. And then of course there's a joke on here. The question being, what is the unit of power? And then the answer being, yes, it is. Okay. Another nerdy joke for you, since we're on nerdiness. Do you remember last time we were talking about, I did the basketball, tennis ball, and the tennis ball went flying up very high. So I dropped it from a certain height from rest, and somehow the tennis ball disobeyed the law of conservation of energy and went much higher than the height that I had dropped it from. So we wanted to analyze it, and I had a run at a time. So let's do that now. Okay. So we can start off with a 0.5 kilogram basketball and a 0.05 kilogram tennis ball. They're close together, but maybe a tiny little gap separating them. They're dropped from a height of 0.82 meters. And then how high does the tennis ball bounce in the end? So we divided it in segments of motion. Segment 1 is that free fall. Then segment 2 is what's technically called an elastic collision of the basketball with the floor. And in this case, what it means is that kinetic energy of the basketball is the same before and after. Nothing is lost there. But oddly enough, when you collide with the floor, since it's connected to the Earth and the Earth forms an external impulse, the momentum of this collision is not conserved. The basketball, in fact, reverses its momentum, but with the same speed. Then it hits the tennis ball, which was still moving down. So at this point, you've got a head-on collision between a downward moving tennis ball and an upward moving basketball, because it's just after the basketball collided, if that makes sense. And then after that, the tennis ball goes up and stops when it gets to rest again. Okay. So we divided motion into segments. That segment 1 gave us that the speed of both the balls just before they hit the ground is negative 4.0 meters per second. And then the segment 2, that elastic bounce with the floor, is just it just reverses the momentum of the basketball, but not changing its kinetic energy, so not changing its speed. So you get plus 4. And then this is the tricky one where we're going to use this collision equation. So you've got an upward moving basketball colliding with a downward moving tennis ball. And they're both going at 4 meters per second. Basketball is going up, tennis ball is going down. Whoop. Question is, what is the speed of the tennis ball immediately after the collision? So I am going to say, I guess 1 is the basketball and 2 is the tennis ball. Yeah, this is just not going to work. So I'm removing the mask. Put it on a little later. Okay. And here are those equations which I recommended go on your aid sheet for the final velocity of ball 1 and ball 2 when ball 2 is initially at rest, which it's not in this case. So 2 is going to be the tennis ball. But I'll show you the trick that we do in physics. When neither of the balls is at rest, what you do, so let's draw it out here, The initial situation is you got ball 2 going downwards, V2 initial equals negative 4 meters per second. And ball 1 is going upwards, V1 initial is equal to plus 4 meters per second. And then finally, what you'll have is ball 2 will be going up, probably. V2 final is question mark. And ball 1, not sure which way it'll be going, but maybe V1 final. Okay. That's sort of what we're trying to find. Although we don't really care about V1 final. Don't care. For some reason, nobody cares what happens to the basketball. But what we have to do, the trick here, is let's switch to a reference frame in which ball 2 is at rest. That's how you solve this. And then you can still apply these same exact equations because the collision still happens in whatever reference frame you're in. Any inertial reference frame is going to obey the laws of physics. So during this collision, we're going to switch to the downward moving frame that's going down at 4 meters per second so that it looks like the tennis ball is at rest. Then we'll use these equations, solve for the final speed of the tennis ball, and then switch back to the lab frame. To do this, since it's going -4, you just add +4 to everything. To do this, add +4 meters per second to all the velocities. All, I guess, y velocities, or y components of the velocities. Okay, and then don't forget, remember to minus the 4 at the end before you display your final answer. -4 meters per second from final answer. And this is what we do in particle accelerators a lot. Normally you'll have particles in the beam one going counterclockwise, one going clockwise, and you collide them. In order to do the analysis, you always switch to the rest frame of one of the particles, which you call the target, even if it is moving. So the analysis is easiest done in the ball to rest frame. I guess initial. So V2 initial prime, I'll call it, is equal to 0. So V1 initial prime is equal to the 4 plus the 4. So now the basketball is coming up at +8 meters per second in the tennis ball reference frame. Does that make sense? And then you just use these equations. The one we care about is V2 final. We're going to use that. And don't forget it's prime because we're in this primed reference frame. 2 m1 over m1 plus m2 times V1 initial prime is equal to 2 times 0.5 is the mass of the basketball, times 0.5 plus 0.05 times 8. And you get V2 final is equal to 14.5 meters per second. But that's still in that primed reference frame, so don't forget, last thing, convert back to the lab frame. So we get what the tennis ball is really doing relative to us. V2 final without the prime is V2 final prime. We added +4 to get to that reference frame, so now we're going to minus 4 to get back to the lab frame. So it's only 10. V2 final equals plus 10.5 meters per second, which is actually pretty fast. So if you just look at it from the tennis ball's point of view, it goes down just before it hits the ground. It's going down with 4 meters per second. After the collision, it's going up with 10.5 meters per second in the lab frame. So that's why it goes way, way up, higher than where I dropped it from. Sort of faster than you would expect, which is why this is a kind of a cool party trick to do. So on the way up, it starts with 10.5, and you can use conservation of energy or your favorite kinematic equation to find that the final height's 5.6 meters, quite a long way up. And so the balls were dropped from 0.82 meters above the ground, but if all the collisions were elastic and no energy is lost, then the tennis ball reaches a final height of 5.6 meters. Okay. And we have, just while we're at it here, I'm going to switch quickly to our little, here's the child. And here are various poppers. These are just showing sort of a, is that me? One of these microphones, maybe, it was the camera? Okay. So this is showing how you can store elastic potential energy, and then it will eventually do some work. Oh. You have to kind of give it a little, okay, it jumps. Also, I had one of these guys. This is one of my favorite things when I was a kid. I got a Happy Meal from McDonald's, and it had these little, they're called poppers. You have a suction cup. Mine was Mario, actually, when I was Well, it's little. You put it down, and it, whoop, you let it go. Maybe it needs to be just a little. Oh. That doesn't want to work. Let's try this one. It used to sit there. The one I had when I was a kid, there's an eyeball one. That's a good Halloween one. It used to sit there for a couple of minutes, and then it would, or even 30 seconds or something, and then it would just suddenly jump up. So what we're doing is we're applying force times distance, and we're squishing that spring, doing work on the spring. It stores some kinetic energy, some elastic potential energy, and then when you release it, jumps way up. All right. Okay. So elastic potential energy can then get converted to kinetic. All right. How's it going out there with Tiffany?
There's one question, but it's not to do with any of this.
Well, you might as well read it since you've got the mic on.
It says, Baby Yoda here. I would like to ask Professor Boba Fett on this Halloween if we are studying the physics behind lightsabers dueling and if we get an in-class demonstration. I would like to wield a lightsaber and to try to deflect Boba Fett's lasers. Thank you.
Oh, yes. Amazing how lightsabers can do that. Well, thank you, Baby Yoda, for that question. We'll just defer it for now. We're going to go on and to, I guess the next 2 units, 7.8 is on power, which has a very specific definition in physics. It just means some work done divided by amount of time. And you hear about engines being measure horsepower, that kind of thing. And then the last section, 7.9, is on gravitational potential energy in space. Okay, so we already had gravitational potential energy, which is just this mgh, but then it's not mgh if you go to space, and so we'll talk about that. So power is a measure in physics of how fast work is done. And so work done divided by the time interval. The unit of power is joules per second. Okay, unit of energy is joules. That's the unit of work divided by seconds. And then we also have a name for that called the watt, named after James Watt. And a kilowatt is 1,000 watts. So here we have someone climbing the stairs at some speed. There's going to be the work that she does is going to add to her kinetic energy and add to her gravitational potential energy as she gets up. So let's do learning catalytics, shall we? Should be on your telephone. 413-380-86. Rita raises a 10 kilogram package at a constant speed to a height of 2.5 meters in 2 seconds. If she were to raise the same package to the same height in 1 second, then how would the work that she did change, and how would the power that she did change, or would it change? What you guys think about that? Let's give it a minute.
We did get a good question.
Sure.
It says, how do we know when we should switch to a reference frame where one ball is 0 and doesn't matter which ball we choose?
Yeah, that's a great question. So yeah, when we're doing collisions, an elastic head-on collision, then you have those special equations on your aid sheet that didn't really derive. And so they only work if the ball that you label as 2 is initially at rest. So V2 initial equals 0. It has to be in order for those equations to work. And so all you do is you label the 2 balls. When you do that, then you switch to the reference frame of the ball that you labeled 2. And you can use those equations. It's a little shorthand trick. I'll time you for a minute. Think about this question and just check with if you could just pair up, check with your neighbor to make sure your neighbor's answering the same thing. Well, thanks. Baby Yoda makes it. Okay. Going once, going twice. Stop delivery. Oh, we never plugged it in. Top 2. So many wires. It's hard to think when you're wearing a Boba Fett costume. A lot of you are voting for B. I think that's the one that I liked as well. So, yeah, basically the system here is the package. So I guess it's just P is equal to work divided by delta T. And so work, I might just call it delta UG or something, M times G times 2.5, 2.5. Anyway, it's going to be the same for both because they're both changed their height by the same amount. But since power is work divided by delta T, if you divide it by 1 second instead of 2 seconds, you get double the power. So delta T goes down for the same work, then the power is going to go up. So you sometimes hear about electric power, and we'll talk a little bit more about that. Professor Harlick will talk more about that in Physics 132 when she's teaching electricity and magnetism in the next semester. But a watt is a joule per second. If you look at your electricity bill, you see that you're getting charged for kilowatt hours, or a kWh. So that's a unit, it's a non-SI unit of energy. And it actually means some number of joules. A kilowatt hour is the amount of energy that you use in 1 hour if your appliance is running at 1 kilowatt power. So you take 1,000 joules per second, that's how much a kilowatt is, and then you multiply it times 60 minutes in an hour and 60 seconds in a minute, and you get 3.6 million joules. So it turns out that a Newton is a pretty small force. It's like 100 grams. Of course, it's a small little force, like how much maybe I'm pushing Baby Yoda, 1 Newton. A joule is a very small amount of energy. Sort of the amount of energy you put in something if you're pressing with 1 Newton for a distance of 1 meter. Not very much energy. And so it's not a very convenient unit of energy to use when you're selling electricity. So they do kilowatt hours, which is 3.6 times 10 to the 6 joules. But it's a type of joule. This is where energy in Ontario comes from in 2022. It varies a lot from year to year, but we have these dams, basically, Niagara Falls and a couple of other water dams in Ontario where there's some water at a high river and then it goes down to a lower river, and you take that water and turn a turbine with it, and that will generate a lot of our electricity. And then there's these gas plants where they burn a fire, but boil water, turn a turbine, that also generates electricity. There's nuclear power plants. 34% of our energy, actually the biggest slice of the pie in 2022 is from nuclear. So that's where you have some sort of fission reactor, which is taking these highly radioactive elements and allowing them to decay at a certain rate, which again creates a lot of heat, again boils water and turns a turbine. And then eventually you have to dispose of that nuclear waste, but nuclear reactors create that. There's also these wind turbines. You might see them around in the countryside. Solar power, 1%, and biofuel. So sort of shows, sort of interesting. Okay, we already did that. The price of electricity, when you purchase it, is 17 cents per kilowatt hour. And so here's an example. You use your dryer. Your dryer says 500 watts on the back, or 5 kilowatts or something. And you run it for an hour. How much should that cost? Well, you can just figure that out. The rate, I guess. Rate, I would call it, is 0.17, like dollars per kilowatt hour. And the cost that you would pay is going to be the rate times the energy, which is the rate times the power that you're using times the delta T. So the longer you run the dryer, the more you pay. But it's going to be, so the rate, 0.17 dollars per kilowatt hour, multiplied times 5 kilowatts times 1 hour. And I get a calculation here, 0.17 times 5, 85 cents. So $0.85. Not very much. Okay. How are we doing? Doing great. Let's go to another learning catalytics question. You've got a car which accelerates from 0 to 30 miles an hour in 1.5 seconds. How long does it take to accelerate from 0 to 60 miles an hour? I'm not using SI units there, but it's just double. Assuming the power of the engine to be independent of velocity and neglecting friction. So I think what I'm trying to say here is that independent of velocity, it's not quite true, but I guess assume power is constant. To get a rough idea here. That's your minute, but hopefully a lot of you have figured out I'm actually asking about kinetic energy in this. Make sense? Okay, so let's I'm gonna just stop it real quick here. I'm gonna tell you, I stopped the whole session. Pressed the wrong button. That was bad. Let me try it again. This has now changed the I don't know if you guys actually do need to know what the number of the session is. Do you? I always post it because people have told me they have to type it in. But it just changed because I accidentally pressed the wrong button. But I want to do this one again. And what I want to tell you, going back to this, is that it is either, I think the two most popular choices were B or D. So the idea here is that the work done on car equals the change in energy of the car. Okay. So somehow, it's kind of strange how momentum and energy work. For example, in the example of the basketball hitting the floor, the energy was the same before and after because there were no losses during that collision with the floor or the tennis ball. If it bounces up to the same height I dropped it from and there's no losses, the kinetic energy doesn't change, but the momentum reverses. When we talk about a car speeding up, where does its momentum come from? Well, I told you before, it's the static friction force from the Earth changing the momentum of the car. Because the Earth, again, is big, and so the momentum can change. But the energy of the car cannot change. What will happen is that you'll use up some chemical energy in the engine by burning the fuel, and that will turn into what kind of energy? Kinetic. Okay, someone in the front row is offering up that's the whole point. Step on the gas because you want to give your entire car this 1/2 mv squared, this kinetic energy. And the work done equals the energy that the car picks up. So this is my question, is if you double the time, but it's the same power, I think you're going to double the work done, aren't you? Nope, wrong. It's not a double. Yeah, so that's sort of the question. You have now doubled your final speed. So I'm going to give you. Sorry, is it back? Yeah, it's back. So since I lost it, I just want you guys to click in again. And I'll discuss it. Is it working? Anyone who wants to yell at me can always do so. You just got to yell loud right on here. Yep. Sure. Yeah, sorry. Yeah, I'm so sorry that the ID code has changed here. It's 171-279-27. Okay. You guys got it? Great. Okay. Has everyone had a chance to re-click? I'm liking what I'm seeing a lot better now. All right. Going once, going twice. Ice type stop delivery, not stop session. And the answer I'm looking for is D. It's 6 seconds. It's going to take 4 times longer to double your kinetic energy if the power is the same. That's what I was trying to get at. So a way of looking at it mathematically would be to say that power is equal to the work, the external work or something, I guess, or just the work, divided by delta T. That's a constant. And so delta T is equal to this work divided by power. It's going to be 1/2 mv final squared divided by the power. So if Vf is doubled, then the delta T will have to go up by a factor of 4. V final squared goes up by a factor of 4. So delta T2 or something equals 4 times delta T1. 4 times 1.5. So sorry, 6. Good? Okay. That's it for the power questions. Okay. And we're exactly on time, so it's good. Okay. So we're going to go back. I think I already mentioned this, that gravity in space looks like this GMM over r squared. So gravity is an attractive force between any two masses. It just happens to be that here on Earth, the most important mass that's nearby is the entire Earth itself. And when you combine that tug of every single rock and pebble and tree on the entire Earth, including the center of the Earth, you end up with a gravity force which is towards the center of the Earth if you're near the surface. And it's the mass times 9.8. And so 9.8 is g times the mass of the Earth times the radius of the Earth squared. That's lowercase g. Uppercase g is this universal constant that you don't use too much in this class. 6.67 times 10 to the minus 11. Okay, so that's the force. Gravitational potential energy also exists between any two masses. And it looks very similar, except two important differences. One is that there's a minus sign, and the other is that instead of GMM over r squared, the potential energy equation, that was for force, for potential energy, it's GMM over r without the square. And we have chosen here the 0 point of potential energy to be at r equals infinity. So just what I mean by that is, you know that the limit as r approaches infinity of 1 over r equals 0. So that would be the 0 point. Okay. And you would note, what else? That this equation gives the potential energies of two masses when their centers are separated by a distance r. So this is negative. Let me just quickly go through this. The gravitational potential energy is 0 when objects are an infinite distance apart. So the only way to add positive energy to a system and have it become 0 is if it starts off with negative energy. So you have to, if you separate two objects, you're actually adding gravitational potential energy. For example, if Baby Yoda is on the floor, there's some distance between Baby Yoda and the Earth. If I increase that distance by pushing them upwards, then I'm increasing gravitational potential energy. So as you're increasing that r distance between them. So it's weird. That's why it's negative. You've got the work done by lifting something is positive, and the gravitational potential energy was initially negative. So if you were to lift that Yoda all the way to infinity, you would end up with 0 potential energy. You separate two objects. So again, there it is. And we'll talk about this a little bit, but let's do quickly this one more, learning catalytics, and I'll give you the actual, if you don't have it already. 171, 279, 27. Whoop. So these are two planets. So you imagine that they're the only two objects in the universe. In one configuration, they're close, and in configuration B, they're farther apart. So the question is just simply, which has more gravitational potential energy? Check your neighbor. It's a pretty quick one. Okay, that's your time. You click in 5 seconds, please. 4, 3, 2, 1. This is a very controversial one. Just show you what the screen's looking like. 55% voted for B has more, and 44% voted for A has more. So let me talk about this. Actually, R is on the denominator. So G times M divided by R decreases if R increases. But that doesn't make any sense because, as I said, as you do work on a system to separate these two objects that are attracted to each other, you're doing positive work. So you must be increasing the gravitational potential energy as you separate them. So intuitively, I think as things get farther apart, you have to be increasing gravitational potential energy. And it's correct because it's less negative. There's a minus sign. UG without the absolute value is less negative, and that means more. So it is, quote, more, meaning closer to positive infinity than minus infinity. That's what I meant by that. But also intuitively, if you have to push on something and do positive work to separate it, you're adding to the potential energy. Are we good with that? Tiffany, we're good in the thingy? Okay. Good. So it's a weird equation. I thought I would just go through it really quickly here. How can two equations, and I asked you this a couple days ago, that look so different be describing the exact same thing? So let me actually work it through here. We'll do an epsilon proof. So if we times this by like 1 over the radius of the Earth, and times top and bottom by 1 over the radius of the Earth, then what you get is negative G ME times M divided by radius of the Earth divided by RE over RE plus Y over RE. So this exact equation gives negative GME times M divided by RE times 1 over 1 plus Y over RE. So that's the exact equation. And if we set epsilon is equal to Y over RE, that's a small number. Epsilon is much, much less than 1 in this case, because some change in, or some height above the floor, Y, is much less than the radius of the Earth. And also lowercase g is equal to capital G times mass of the Earth divided by radius of the Earth squared. Remember that? That's the 9.8. So that means that capital G times mass of the Earth divided by RE without the squared just equals G times RE. So we can rearrange this and get that U sub G is negative G RE, that's all that stuff, times lowercase m, times 1 over 1 plus epsilon. And now the trick with this is you just times the top and bottom by 1 minus epsilon. I don't know if you've ever done this. But if epsilon's small and you have a 1 over 1 plus epsilon, then what you get is 1 minus epsilon on the top and 1 minus epsilon squared on the bottom. That's a man. 1 minus epsilon divided by 1 minus epsilon squared. And since epsilon is much, much less than 1, then epsilon squared is very small. It's negligible. Anytime you've got a small number, and you square it, you can kind of neglect the squared term. It's called a first order approximation. So what this means is that 1 minus epsilon squared is approximately equal to 1. So U sub G is approximately equal to, let's do it more carefully, approximately equal to negative G times RE, radius of the Earth, times the mass, times 1 minus epsilon. So you can expand that out. It's negative GRE times M plus G times RE. Don't forget epsilon is just Y divided by R sub E. So these cancel. And you can just set, if you want, equal to u sub 0, then this is some arbitrary 0 point plus mg times y. Arbitrary. So if you're ever using the change in gravitational potential energy, turns out mg times y is the exact same thing as negative capital G times mm over r. They seem very different, don't they? But one's an approximation of the other. And I could quickly just do it with a cat, actually. Climbing the CN tower. 5-kilogram cat starts at the ground, the base of the CN tower, and it goes up 350 meters. So you can use the approximate equation and calculate the change in joules of the cat. Starts at 0. At the final height of 350, he's at 17,000 joules of energy in the cat. Okay, so that's the old way. If we use this new way, the exact equation, using the correct equation, you can calculate the change in potential energy. But don't forget, the base of the CN tower is 6,371,000 meters from the center of the Earth. And then the restaurant, if the cat goes up to the restaurant, it's 6,371,350 meters. So if you minus those two things, I don't know if you can believe me or not, you get 17,000 again. This is something you kind of have to do in your calculator. Okay. Where are we at here? I wanted to do one more. Let's go through that. Yeah, escape velocity. So people have considered, this is a gun which can shoot an aircraft into space. There is some idea that if there was no air resistance or something, then we have this law that what goes up must come down. Well, if you have enough kinetic energy or enough velocity or something, then it'll never come down. So question is, what is the minimum speed that you have to launch something at the Earth's surface so that it completely escapes Earth's gravity? And the way you solve this is with conservation of energy. You say it has some initial kinetic energy and some gravitational potential energy, which you're going to use the exact equation, G equals UG equals negative G times m over r. As r goes to infinity, the final energy must be 0. So you just make the initial energy also 0. And that's how it works. So we do it like this. Initial. You've got V initial on Earth's surface. So you've got R is equal to R sub E. We're going to neglect air resistance, which resistance. And then we're going to do finally, you're in deep space. R approaches infinity. Okay, and then V final equals 0. It goes out to infinity and then it stops. You can imagine that. Or when it's very far away, it has negligible velocity, something like that. So the diagram stage looks like this. If you look at kinetic initial plus UG initial plus the external work is K final plus UG final. Then this is 0. And the kinetic energy initial is positive, and the potential energy initial is the same negative, and everything else here just equals 0. So you've got 1/2 m times V initial squared minus G mass of the Earth times the mass of the object divided by R without the squared plus 0 equals 0 plus 0. So I think you can divide both sides by lowercase m, doesn't matter. You get V initial squared divided by 2 is equal to G, mass of the Earth, divided by the radius of the Earth. So V initial is just equal to square root 2 times G times mass of the Earth. It's a little bit different than the circular orbit thing. I think it's going to be more. 2 times 6.67 times 10 to the minus 11 times the mass of the Earth, which is, I think it's 5.97 times 10 to the 24. And then I'll divide it by radius of the Earth, 6.4 times 10 to the 6 without the squared. And I got 11.1 times 10 to the 3 meters per second. So V initial is 11 kilometers per second. This is called the escape speed of Earth. Okay. I think the circular orbit speed was something like 9. So when you get up to 11, then you're no longer in a circular orbit. You can actually escape all the way to infinity. So every object, depending on its mass, a higher mass object, you'd have a higher escape speed. If you have a more dense object, so its radius at its surface is less, then you get a higher escape speed. So what people imagine is if the Earth was much smaller but had the same mass, you'd have a higher and higher escape speed. At some point, you could have a black hole. If the mass of the Earth were large enough, or if its radius was small enough, you could actually get the escape velocity to be the speed of light, or greater than the speed of light. And since nothing can go faster than the speed of light, then nothing can escape the Earth at that point. So this is what's called a black hole. A black hole is any star or any planet or anything such that its mass is so large or its radius is so small that you would have to go faster than the speed of light to get to this escape speed. So by the laws of physics, nothing can escape it. So anything that enters a black hole can never come back out. Okay. Yeah, you're right. I'm sort of at the end here. We're going to start in torque, chapter 8. We're going to finish up chapter 8 before the term test when we come back from reading week, but I'll see you guys on Wednesday.